Hey everyone, welcome back to the channel. This week I've reached week 3 of the CS50x course, and it was all about algorithms. We dove deep into concepts like sorting, searching, recursion, and more. So in today's video, I'll break down the key ideas, how I understood them, and how I use them in the problem set. Let's start with running time, or in simple terms, how fast or slow our code runs depending on the input size. Here are the three main notations we learned. Big O describes the worst case performance of an algorithm. Omega describes the best case performance, theta. When the best, average, and worst cases are all the same, we can say the performance is exactly that. Think of big O as the upper limit. The worst thing that could happen, omega is the opposite, how fast it can be in the best case, and theta is when you're locked in on performance no matter what. Now let's explore searching algorithms, how we find specific data within a collection. We started with linear search. With linear search, we simply go through each element of an array, one by one, until we find what we're looking for, or we reach the very end. Worst case, big O of n, we might have to check every single element in an array of items. Best case, omega of 1, if we're lucky the item is right at the beginning. Theta, undefined, because its performance can vary so wildly. And if the element isn't there, yep, we still have to check everything just to be absolutely sure. Next, we stepped up to binary search, which is significantly smarter. It works by repeatedly dividing the search space in half. Worst case, big O of log of n. This is because with each step, we cut the problem size in half. If you have an element, it takes log 2 of n steps to narrow it down to 1. Best case, omega of 1, again, if the item is the middle element on the first try. Theta, also undefined. This makes binary search incredibly fast, especially for large datasets. However, there's a crucial condition. The list must be sorted for binary search to work, which brings us to sorting. The art of arranging elements in a specific order is where we went next. Let's start with selection sort. With selection sort, we scan through the unsorted part of our list, find the smallest element, and then swap it into its correct position at the beginning. We then repeat this process for the remaining unsorted portion. Worst case, O of n squared 2. We perform roughly n comparisons for the first element, then n minus 1 for the next, and so on. This sums up to about n multiply n plus 1 on 2, which simplifies to O n squared 2. Best case, omega O of n squared 2. There's no performance improvement even if the list is already sorted. It still goes through the full comparison process. Theta n squared 2 is consistently quadratic. Then came bubble sort. This algorithm compares adjacent pairs of elements and swaps them if they're in the wrong order. Each pass through the list bubbles up the largest unsorted item to its correct position at the end. Worst case, O of n squared 2, similar to selection sort, it requires many passes and comparison. Best case, omega of n. This is where bubble sort shines a little. If the list is already sorted, we can add an optimization. If no swaps occur during a pass, we know the list is sorted and can stop early. Data, not defined. While it can be optimized, bubble sort isn't usually the top choice for large datasets. CS50 perfectly illustrated this with the Mario brick example. You start with a simple base case, like printing one brick, and then the function calls itself to build up the entire structure, line by line. And recursion isn't just for drawing. It's incredibly useful in algorithms, like in the next sorting technique. Merge sort. Worst case, big O of n log n. Best case, omega of n log n theta n log n. This makes merge sort incredibly efficient and stable, which is why it's a go-to algorithm in many real-world systems. Now for the most hands-on part of the week, the problem set, we tackled the runoff election simulation. We had to build a program in C that simulates a preferential voting system. Voters rank candidates in order of their preference. The program then determines a winner based on a set of rules. If a candidate gets over 50% of the first choice votes, they win. If not, the candidate with the fewest votes is eliminated, and their votes are redistributed to the next preferred candidate on each ballot. This process repeats until a clear winner emerges. It was a fantastic challenge that combined all the algorithmic concepts we learned with practical C programming and complex logical thinking. Definitely a highlight of Week 3. Week 3 of CS50x was an exciting roller coaster. Diving into algorithms, understanding their efficiency, and then applying them to solve a real-world problem like the runoff election was incredibly rewarding. If you're also taking CS50x or just learning to code, let me know how Week 3 went for you in the comments below. I love hearing your experiences. Don't forget to like this video, subscribe for more coding adventures, and hit that notification bell, because next week we're tackling a huge topic: memory. See you then.